All right. Hello, everyone. Sorry for the delay. There are certain things out of my control, and there are certain things in my control. Both of them went wrong. All right. So, welcome to lecture 6. We are almost there. Today we are going to talk about some interesting stuff. Hopefully, you also find the lecture interesting. So the main content of the lecture is a follow-up to the dynamic pricing for single value buyer, the Leighton-Kleinberg paper that we discussed in the last lecture. And we are going to see how to basically extend that setting to a multi-dimensional version with applications in feature-based dynamic pricing or personalized contextual dynamic pricing, and also personalized medicine. So the problem we are going to look at, which is that generalization, is called contextual search. I'm going to start by the basic setup, some simple definitions, and explaining two types of loss functions that are relevant in this application. In particular, we're going to talk about what they call the symmetric loss, and the other one, which is more related to revenue management, the pricing. Then we try to design algorithm for this problem for both of the loss functions. So as a warm-up, we look at the two-dimensional version of contextual search. And then you will see a potential function argument with a lot of geometric intuitions, potential function argument, which is backed by basic elementary geometry. To see how to design a near optimal algorithm for two-dimensional contextual search. Then we switch to the actual problem, which is the multi-dimensional version. And by the way, so the warm-up is just going to be focused on the symmetric loss. But then when we switch to the multi-dimensional version, I'm going to talk about both loss functions. And then in order to design this algorithm and also analyze it, we need to learn a few very basic things in algebraic geometry. So some basic notions in algebraic geometry. In particular, I'm going to talk about Minkowski sums, the very basic definition of intrinsic value, and how they are related to a polynomial called a Steiner polynomial. So some basic notions in algebraic geometry. So in particular, we are going to talk about a Steiner polynomials. Don't get intimidated. These are really easy. And I don't assume any background about it. So I'm going to cover everything. And then we see how to design the optimal algorithm for both loss functions. So this is roughly the plan. Let's start from so what is a contextual search problem? Imagine you're a decision maker, so you should think of yourself as a seller that is setting a price to a buyer that is arriving, or you can think of applications such as personalized medicine, when as a decision maker, you are trying to identify the right dosage of a medicine. So there is a target value that you are not aware of. For example, in the revenue management setting, it's the value of the buyer. In the personalized medicine, is the right dosage of the medicine. And you try to identify that through multiple interactions with buyers, different buyers that are in over time. And these buyers can be identified with different feature vectors. So the theta at each time t a new user with context vector or feature vector context xt arrives, and imagine xt is a d-dimensional vector. So the way to think about it in the personalized medicine, so there is a patient that arrives, the patient has different features, age, race, preconditioning situation, the blood pressure, etc. And you get to see this context. In the dynamic pricing, it is the features of the buyer. We are personalizing the prices, so we get to see the features of the buyer. And then there is an unknown target. But this value is personalized, so it depends on the context. So the way we think about it is that basically the value at time t is the dot product of xt and some unknown parameter vector. I'm going to use theta for that. So theta is unknown. So you should really think of it as how the different features are aggregated to specify the right amount of the target value. For example, in the dynamic pricing problem, how the different features of the buyers are aggregated to specify the value of the buyer for the item. In the personalized medicine application, how the different features of the patient are aggregated to specify the right dosage of the medicine for that patient, and you don't know theta. But then you get to see the context, and you can experiment with the patient, with the buyer. So how would you experiment? So your experiment is basically guessing the value VT. So your experiment is going to be, you send a query for guess equal to P of t. For example, you set some dosage amount for the medicine, or you set a price. And then you get to see a binary feedback. So binary feedback is revealed. So you get to see basically the indicator that the value VT is greater or equal than the price. Okay, that's the only feedback we receive. And the goal of the decision maker, so the goal is to output in an adaptive fashion a series of decisions, aka queries or prices P1 to Pt, such that we minimize some sort of loss. So we are trying to minimize summation t from 1 to capital T. Let's call that the loss, and I'm going to define this function. So loss of two quantities. The first one is the Vt, and the second one is Pt. But this loss function, so this loss function can have different choices. So for example, let's say, let me define so this is the loss function at time t. So we can define two forms of losses which are relevant to the applications that we discussed. The first one is what I call the symmetric loss. So the symmetric loss between the value v and a guess p is basically equal to the absolute value of the distance between the value and the guess. And note that the value depends on the true parameter guess and the context, and the guess depends on the context as well. But you can define the function this way. Then another definition, the pricing loss. Basically, the loss that you get if you, in terms of revenue, if you knew the value. So if you know the value, then you set the price equal to the value and you extract the full surplus. So that would be your maximum revenue if you knew V at the first place. And then if you set the price, then your revenue is going to be P if the value is above P, otherwise it's going to be 0. So the difference between the two defines the pricing loss. So loss of V and P is basically equal to V minus P indicator that V is greater or equal than P. So the first loss function is highly symmetric, and the second loss function is highly asymmetric. In fact, if you underprice, meaning that you go with prices smaller than value and you mess a little bit, then you are not going to lose that much. You lose as much as you underprice. But then if you overprice, all of a sudden your loss becomes gigantic because your revenue in a matter of a second becomes 0. So in some sense, when you work with pricing loss, you need to be a little bit more conservative with testing the prices. So you want to test prices that are below the value more versus prices that are above the value. You don't know that, but you kind of have more flexibility in experimenting lower prices versus higher prices, which is somehow similar to what we saw last time when we were talking about Kleinberg-Leighton dynamic pricing algorithm, the double binary search option. Okay. Some assumptions about the model if it's not clear. Some assumptions. I assume you start with a very basic knowledge set about the parameter theta. So I call that S1, and you will see in a second why it's called S1. S1 is equal to, let's say, 0, 1 to the power d. And we know as a fact that theta belongs to S. So that's assumption number 1. Assumption number 2, which is really not an assumption. We assume the sequence x1, x2 to x capital T is picked by an adaptive adversary. So even the adversary can be adaptive. So the sequence x1 to xt, I am not making any assumption on that. I assume it's adversarial. Okay, is the setup clear? Now, given an algorithm for contextual search, with either of the loss functions, we can define regret. So the regret of the algorithm, let's say, fix an algorithm. Then the regret of the algorithm is defined to be basically, so the minimum loss is 0. So it's basically the loss that it accommodates. The summation T from 1 to capital T, LT, and I'm adding this extra notation. So LT is basically the loss that the algorithm gets at time T. So L of the dot product with theta and xt, which is the VT, and the query or price that the algorithm has posted at time T. Okay. So we try to design algorithms that have a small regret. Good. So if you look at the very special case, it's not really a special case, a very special case. Where d is equal to 1. D is equal to 1. Then the problem loses the context, yes.
I can say when the adversary is adaptive, then there is no use to use random algorithms. and then it would be equivalent to non-adaptive adversary treated.
Here we're not going to use any random because of that.
Why is it called regret here? Is as opposed to just like a loss?
Well,
Because
so
regret
it is regret because there is a decision. So if you knew theta, given any context, you could just query VT, and then your loss would have been 0. So in hindsight, if you, for example, you knew the unknown parameter theta,
So is this implicitly comparing it to like the best
the best algorithm in quote unquote hindsight, which always gets loss 0. And hindsight here is really referring to the case that you know the unknown parameter. So if you know the unknown parameter theta, you are not going to incur any loss. So the inherent loss of the problem is 0. That's why we call it. All right, so d equal to 1. So first of all, is it clear then when we look at the one-dimensional version of the problem, the notion of context doesn't matter anymore? Because think of it, right? So this is just like one scalar. So v of t is xt times theta. You just don't know this is a scalar, and then you post some p of t. So replace p of t with p of t divided by xt. So it is really about you post some number, and if it is greater than theta, you get the positive feedback, less than theta, you get the negative feedback, and then the loss function has the same form. So if you normalize by the context at each time, then for one-dimensional version of the problem, context doesn't play a role. So the problem becomes more or less like the pricing loss will become the direct pricing problem that we saw in the last lecture. And then for the symmetric loss, it is even a simpler problem. So there is a target value that you don't know. You query something, and then your loss is going to be the distance between that query and the target. And your goal is to use an algorithm in order to minimize the recurrence. Okay. So for example, for d equal to 1, let's say I focus on the symmetric loss. What is the algorithm that gives you constant recurrence? So binary search gives you constant recurrence. That doesn't depend on capital T. Let's see why. So binary search. So what does binary search do? So binary search at each time keeps track of a knowledge set that starts with the interval 0 to 1, and always query the midpoint. Based on that, you update the knowledge set to the correct one, and then you continue. All right. So how many? Okay. So let's say you're at iteration k of binary search. Then if I keep track of the knowledge set S of t, which is the set of all possible thetas up to this point given the feedback I have received, what would be the coordinate of this set? So the algorithm is simple. I assume everyone knows binary search. I didn't explain it. So let me clarify. So I have 0 to 1 as my search interval. I query the midpoint. Now, if the binary feedback is plus, that means the actual target is above the midpoint, otherwise it's going to be below the midpoint. Based on this feedback, I switch to the upper half or the lower half, and we iterate. So knowledge set will be updated at the beginning of interval 0 to 1. After you query the midpoint, it's going to be either the upper half or the lower half of the interval. After k iterations, what will be the size of the knowledge set? So it is at most half to the power k minus 1. Is it clear? After power k, after k iterations, so right? And then at time t, what would be the maximum symmetric loss that you might incur? So your price is the midpoint of the knowledge set. So I claim that L of t is at most a coordinate of S of t, right? Because you have this interval, you're certain that the target set is in that interval. If you query the midpoint, target is somewhere else, so therefore the loss is bounded by the coordinates.
Divided by 2. Right?
Now, I mean, S of t is at the beginning of the interval. So notice that at the beginning of the interval, let's say.
But anyways, if you pick the middle point.
So then this is going to be k minus 1. Yeah, so S of t, let me write it down. So S of t is going to be the knowledge set at the beginning of the interval. So then summation t from 1 to capital T of L of t is really at most summation t from 1 to capital T of half to the power t minus 1, and this is just a constant. If you even have the summation of t infinity, this is going to be constant. Yes.
So if there's some noise with respect to the target value, is the problem still trivial?
If you have time towards the end of the lecture, I'm going to talk about the noise. But if you have noise, then more or less you can do the same thing as long as the power of the noise is small.
And one more question, but that's maybe not known. This doesn't compete with the best loss in this class. So if my V's were not actually linear, but I can't still compete with the best theta, right? That's maybe not, this doesn't do it, but is it known if that could be done?
Yeah, so for the class of Lipschitz function with some assumption, there is a paper that kind of like does the same thing in that class, but beyond that, I don't know anything off the top. But that's a great question. Like for example, you can think of logistic losses, things of that sort, right? Yeah. So this is for the symmetric loss. Note that this is the symmetric loss. So binary search and symmetric loss.
Isn't the binary search the best algorithm for adversary for the symmetric loss?
Sorry, I didn't
The
hear you.
binary search isn't the optimal
Yeah,
online
it is the optimal algorithm for
the symmetric.
up to some constant for the symmetric binary, for the symmetric one dimension, almost trivial. And then if you look at the binary search, sorry, not the binary search. If you look at d equal to 1 and pricing loss, then we discussed this last time, right? So if you run binary search, meaning that you do the binary search, once the knowledge set becomes smaller than 1/t, you go with the lower price. So if you do that, then we discussed this last time. What would be the regret? It would be order log t, if you remember. And then there was a KL result, the Kleinberg-Leighton result, Kleinberg-Leighton double binary search. Which is really a bad name for it, but let's go this thing. Which shows you can get order log t. In the same paper, they show this is information per type, meaning that no algorithm can do better than order log. The pricing loss is usually more difficult than symmetric loss. Here, there is a dependency on t, and you cannot do better than log t. Here, you can get a constant. But this is the complete picture for d equal to 1. Okay, so now let's think about d equal to 2 and see what is challenging. So before that, let me add a few more definitions. I already mentioned that. So S of t is going to be the set of all possible theta at the beginning of time t, meaning that I have an algorithm. So for each algorithm, based on the feedback I have received from time 1 to t minus 1, I can always define the numbers. All the so let's make this concrete. So S of t is basically equal to S1 intersection with a bunch of half spaces. I'm going to look at it's hard to write it down. Okay, so on the theta prime times x t prime. Yeah, I think what I'm going to say is let me define something for that. So let's say at time t, we get some feedback, right? So the feedback can be either a plus feedback or a minus feedback. So plus feedback means that the p of t that you had was smaller than dot product of theta and xt. And the minus feedback means that pt is greater than theta dot xt. So based on each feedback you get at each time, you can decide which half a space defined by the normal vector xt and constant number pt, the actual unknown parameter theta belongs to. Right? So basically at each time t, I can, so let's define this half a space to be h plus t, and this half a space to be h minus t. Then S of t is basically all the possible thetas that are consistent with the previous feedback. So it's going to be S1 intersection with h of feedback at time t prime. Write it down. So h of feedback at time 1 intersection with h of feedback at time 2 all the way to h of feedback at time t minus 1, when feedback at time t prime is this thing. So f of t is equal to feedback at time t. Is either plus or minus. Is it clear what does this definition do? So I'm just like looking at the previous feedback, look at the intersection of the correct half spaces with the original knowledge set you started with. In this case, it is unit hypercube, and that will give you a knowledge set. So when at time t, I'm pretty sure with probability 1, there is nothing stochastic. So with probability 1, unknown parameter is going to be in the set st. I'm going to define also st plus and st minus. So st plus is just going to be s of t intersection with ht plus. So if the feedback is a plus, then the knowledge set will be updated to st plus. And st minus is s of t intersection with ht minus. So if the feedback is negative, then you update the knowledge set from st to st minus. So in other words, st plus 1 is equal to st of feedback at time t. So if the feedback is plus, it's going to be st plus 1 is going to be st plus. If feedback is negative, it's going to be st minus. Just a bunch of notations because I'm going to use them in the description of the algorithm, etc. So when you think about how to design an algorithm in this domain, you have some knowledge set at the beginning of each time. And then you want to query a point inside that knowledge set for sure. But when I say inside that knowledge set, what do I mean? That means in your head, you pick a theta that is inside the knowledge set, given the context query theta.product x. So you want to query a point that is inside the knowledge set, so that once you receive the feedback and you remove the part of the knowledge set that is inconsistent with the feedback you receive, you have enough progress. For example, you shrink the volume of the knowledge set, or you reduce some potential function that is related to the knowledge. For example, in the binary search, your potential function is the length of the search interval. And then by querying the midpoint, you make sure that once you receive the feedback, when you update the knowledge set, you have enough progress in your potential function. The length of the interval is going to be multiplied by half each time, no matter what type of feedback it is. Okay. So then in your head, you might say, okay, so if, for example, we look at the two-dimensional version of the problem, then I can always maybe query a point such that the volume of the part that I'm shrinking would be kind of a representative of how much loss I get in that round, right? So for example, if we can find a potential function, so let me write it down. So potential function argument. Suppose we find a potential function I call that phi of t, for example, such that at each time t, our algorithm picks a query such that the loss at time t for that query is at most some, let's say, constant c multiplied by phi of t minus phi of t plus 1. So you want to have a measure of progress, aka a potential function. And you make the decision such that in each time you can say the loss you have is at most some constant times the progress that you make. Then you can say, hey, if this is true, then I can use a telescopic summation and say, hey, summation LT, t from 1 to capital T is going to be at most c times my phi of 1 minus phi of t, assuming phi of t is always greater or equal than 0. So you design the potential function that is always non-negative. Then this is at most c times phi of 1. And now the name of the game is having a potential function that at the beginning it is small. For example, if it's constant, you get a constant. You get a constant recurrence. So in the special case of the binary search, for example, the potential function was the length of the interval, and the loss in each round was bounded by the change in the length also, right? Not only it was bounded by the length of the interval, but because you picked the midpoint, it was also bounded by the change in the length. And therefore, the rest of the argument goes through. And when you think about the two-dimensional version, the first thing that comes to mind is maybe my measure of progress is going to be the area, right? So you have this two-dimensional shape uncertainty set. It is going to be a square at the beginning, and then you cut it with half spaces. But maybe you can somehow cut it at each time in a way that you lose a good fraction of the area. The catch is the cuts that you make in each time are the half spaces where their normal vector is determined by the adversary. It's the context that you receive at that. And let's see what can go wrong. So for example, let me draw it on that whiteboard.
May I say something?
Yes.
For the symmetric case, shouldn't we consider our estimation of theta as the center of the circle, the smallest circle that covers our S of t.
But what does the I don't think that works. And one of the two examples I'm going to show is showing you why it doesn't. Let me go to these examples and then we will see what would go wrong. That's meaningful. So you can't, first of all, well, yeah, let's see what can do. All right, so the first thing is that you might end up in this, okay, so example one. Let's say my current knowledge set is a very thin rectangle for some reason. So this is my knowledge set in 2 dimensions. So I'm going to talk about 2 dimensions or something. And then the adversary comes and give you this context. So the context is going to be in this way. Right. And imagine this is extremely thin. It is extremely thin. So first of all, the loss in this round can be actually quite large, right? Because the loss is bounded by kind of the width of the region along this direction. So for example, if the point you are picking is this point, but then the actual point is here, then there will be a huge loss. So the loss can be huge.
Where's the box?
So the box is the uncertainty set or the knowledge set. So this is S of t at the beginning of the time. So it's like all possible thetas that you can think of. So thetas are 2-dimensional vectors, so it can be anywhere here. And then you have the algorithm, so you have to basically pick a query. Each query corresponds to one of these hyperplanes because your normal vector should be xt. And the question is where to put that query. And what I'm saying is if your measure of progress is area, then you're already doomed because the area of this thing is 0. So no matter where you put this, the area itself is going to be 0. It's going to, so loss can be, the upper bound on loss can be very huge. Is it clear why the upper bound on loss can be huge? Because you're thinking about the dot product of theta and xt, where theta is a vector in this set. So if you think about, let's say this is the origin, right? Let's say this is origin. So if your theta is this point, then theta dot product xt is going to be a huge number. The loss can be very large, but then the area of this thing is already 0. So no matter how you cut it, the area cannot change much. So you can't guarantee that the area plays the role of a potential function because even phi t is very small. So you can't have area on the right-hand side of this.
And so log area also doesn't seem like the right.
But perimeter seems to be a good idea, right? So if you think about the 1-dimensional volume, which is perimeter of this rectangle, the area around the rectangle, the perimeter of the rectangle, then actually the perimeter is a good measure for the loss. And if you find the midpoint, then you can say the loss is bounded by the change in the perimeter. Okay, so area is not a good idea to think of it as a potential function. And then perimeter is actually a good idea. Is it clear why the perimeter is a good idea and area is not? Because this is very essential in understanding the algorithm. Yes.
Is it just this edge case where there's 0 area, or are there other cases where
I mean,
it's like clear that the perimeter would be better?
For this particular address, you're absolutely right. So there are cases in which the parameter is not actually a good option and area is a good option, and we are going to see that in a second. But for this example, all I'm claiming is that area is not a good idea because the area of a line, two-dimensional area of a line, is really zero. So you can't measure the progress based on something that is already zero. When your loss can be really huge. But then perimeter is a good idea because, you know, if I try to find the midpoint here, then I can say, well, so the change in the perimeter, which is half of this thing, is always an upper bound on the loss up to a constant, which is the case. So going to Pepe's point. Let's say, again, we have a thin rectangle. It's a little bit thicker than before. And the context this time is in this direction. Okay. All right, so let's say this is W. And imagine you're looking at the dot product of, you know, any theta with xt. So what I'm trying to say is that if xt is bounded by 1, has norm bounded by 1, then somehow your maximum loss is scaled with W, with the width of the context, with the width of the region along this direction. And it's not actually that hard to find a potential function anyway. Actually, area is a good idea. Why? Because, well, so this time, the way that I can cut this, I can define my query to move this hyperplane up and down. And then, for example, if I pick the midpoint again, then half of the area is going to be gone. And the area is scaled with W, so this is good. So the potential function, the change in the potential function can be an upper bound of the loss image. So area seems to be a good potential function here. But then perimeter is not. And the reason is kind of funny because, well, so I claim, let me change the context set, let me change the set a little bit to see that this is not actually a good idea. I want to give you an extreme. Say this is the shape of my set. Then if you say, hey, this is equal to, let's say, L, this is equal to W divided by 2. Okay. So I claim that basically, right. So if, for example, this is my hyperplane, then my area is going to be this thing versus the previous one. So the change in the area, the change in the perimeter will be kind of bounded by the length of this line plus this line minus this line. That's the maximum change in the perimeter you can get. So the maximum change in the perimeter you can get as you move this thing up and down would be this plus this minus this length. And let's actually calculate that. So that would be a square root of L squared plus W squared divided by 4 times 2 minus 2L, which is equal to 2L, a square root of 1 plus W divided by L, a square times 1 over 4, minus 2L, which is equal to 2L times 1 plus a square, I'm just taking something trivial, And then if L is much larger than W, then this is in the order of, so this thing is going to be 1 almost equal to 1 plus half of 1/4 W over L squared. Then this is going to be equal to order L times W squared divided by L squared, which is equal to order W times W over L. So if W over L is very small, then the change in the perimeter here cannot be actually large. And therefore, perimeter cannot play the role of a potential function. So by these 2 examples, I hope I could convince you. So one challenge in the contextual search problem for higher dimension is coming from the fact that sometimes you need to look at lower dimensional volumes. Sometimes you can work with area, like here, which is the 2-dimensional volume in this case, the full dimensional volume in the 2-dimensional problem. Sometimes you actually need to look at the lower dimensional volume, whatever that means. And I'm going to define that in the next half of the course, next half of the lecture. So, and then somehow a mixture of the actual volume and the lower dimensional volume can play the role of the potential function to tell you how to design an algorithm and how to analyze it by looking at the progress of the potential function. If you use either of them, then there are bad examples that kind of say, hey, you can't use that as a potential function. You can't use either of them as a potential function. Or maybe a mixture of them can be a potential function. And let me show you the optimal contextual search algorithm for 2-dimensional. So we're going to work with a potato as the canonical example for the uncertainty set. So we will have this potato here. Yeah, so let's say this is my almost a potato. Yeah. And then, right, let me actually make the potato a little bit skewed to show you. Doesn't even need to be convex. Good. Now, let's say this is S of t at some time t. Imagine this is the direction x of t, where the direction of the context is. Now we can define these 2 points. Let's see what are they. So I'm defining PT bar to be the maximum of xt and let's say theta prime for all the theta primes in my set SD. So it's basically, so imagine I'm looking at lines that are orthogonal to xt and you move them around. So this is the top point that touches the potato. Yes?
And why ST can be non-convex?
I mean, in our problem it's going to be convex, but most of my arguments, they don't rely on convexity. I mean, of course, in our problem, we are thinking about, hey, you start with the hypercube and then you have intersection with half spaces. So it's a polytope, so it's definitely will be convex. But I don't rely on convexity that much. So this is PT bar. And let's define PT underline to be the same thing, but this time I take the minimum theta prime in ST, XT, and theta prime. And then we define the width of the set ST with respect to direction XT to be basically PT bar minus PT underline. So looking at this picture, I guess what I'm trying to say is that right, so this is going to be my double. So this distance is equal to that. And then this hyperplane, or this line in this two-dimensional space, is basically all the theta primes such that dot product of theta prime and xt is equal to pt bar. And this guy is all the theta prime such that dot product of theta prime and xt is equal to pt underline. Do you have a question? Angelina, you had a question? No?
No.
Oh. All right. Let me define something else. Maybe actually I don't need that. Okay, good. So here's an algorithm. This algorithm is going to use phi of t equal to area at time t. This is the area of the potato at time t squared plus, so this is the area. So you look at the square root of the area plus the perimeter, and I'm going to use this as a potential function. So this is the area time t, this is the perimeter at time t. So we want to have an algorithm that uses this thing, that uses this as potential function. Let me define the midpoint also. So I'm looking at PT, let's call it mid. So it's simply PT bar plus PT underline divided by 2. Adding that to the picture, that would be this hyperplane. So it corresponds to all the theta prime such that dot product of theta prime and xt is equal to pt. And now I have a question. Who is ascribing today? Any volunteer? Who has ascribed once? Give me a hand if you. Okay. You haven't ascribed once? Have you ascribed once? You haven't ascribed?
I ascribe to.
Oh, you ascribe 2. Oh, that's interesting. Okay. So you ascribe 2. Are you guys willing to ascribe this lecture? Sure. This is fun. I mean, there are going to be a lot of pictures that you have to draw. You can master, your TXT skill.
I don't know if that's a good selling point.
This is my dark humor. So. Thank you.
Can I ask a quick question?
Yes.
The 2 lines, the PT upper d.log, you're referring to the red line.
Right.
Why are they like this instead of like the width?
So these are 2 numbers, right?
Yeah.
Their distance is what they define as the width. And then you should think of 2 parallel lines. Their distance is width. And the formula for each of them is basically all the theta primes such that dot product theta is. So the normal vector to both of them is equal to xp. Is your question why?
The ST area is for data, right?
So ST is the potato itself.
Yeah.
So so ST is contained in between 2 lines.
Where's the origin of?
Friends,
Do you define origin for the ST?
does it matter? It really doesn't matter. right? Because think of the point that achieves this thing. So it's going to be on this line. And the normal vector is xd. So that point times xd should be equal to pt bar. Therefore, this is going to be this line. It doesn't matter where the origin is. And again, think of the points in SD, this guy that achieves this minimum. So it should be on this line. The normal vector is xd, so it should achieve this equation. And that's how you have this. Yeah, I mean, you can have this anywhere on the 2D plane. Does it make sense? Yes.
Do we use width? Where does width come in?
Yes. So we are going to use it in the algorithm.
I see.
Yeah. So we're going to use it in the algorithm. So I didn't tell you what the algorithm is, right? So let's focus on the symmetric laws.
Is the broad idea to kind of like try to mimic this midpoint by using the average and then like P upper bar and P lower bar kind of like, I mean, they're upper and lower bounds, right? Sort of.
And this is a good idea, but only if you're in one of these examples. Like, for example, if you, I guess what you're saying is I can, always pick this hyperplane, which corresponds to P meet.
Oh, is that not what we're going to do?
No.
Oh, later.
No. I mean, we are going to do it in one case. So because the point of this midpoint is that it's going to actually decrease the perimeter. If you wanted to use the area, you could always find a line such that the area on top of, well, so going with the perimeter is not always a good idea because of this example. So if you are not in this scenario, then we are going to do what exactly you said. If you are in the other scenario, we are going to pick a line that divides the area in an equal fashion. And that's more or less the algorithm. But in order to distinguish whether we are in example 1 case or example 2 case, we need to define something else. So I'm going to look at, so let me define h to be the length of the line segment corresponding to S of t intersection with that hyperplane. So all the theta prime such that dot product of theta prime and xt is equal to pt. Okay, so what is h? Basically, I'm looking at this line segment. Use a different color. I'm looking at this line segment. And let's say this is equal to h. I somewhat try to understand the situation of my potato, whether w is greater than h or w is smaller than h. And based on that, go with 2 different strategies. In one case, I'm going to try to have a strategy that decreases the perimeter. In the other case, I'm going to go with a strategy that decreases area. And this way, I can guarantee no matter which case happens, my potential function's progress will be upper bounded by the loss. That's the idea. So let's try to follow this. And this is a management science paper. You sometimes get surprised to see this stuff in a MS paper. So, what is the algorithm? So we're gonna start with, let me just write down what we do in each talk, right? for t equal to 1 to capital T. So adversary reveals the context. Now we have S1, which is equal to 0, 1 to D at the beginning. Here we look at W and H. So calculate W equal to the width of your current set S of T and the direction xt as written there. And also H. I'm going to look at two cases. So the first case is case 1. W if W is greater than H divided by 2. Yes, that's what I want to do. Greater than 2 times H. Yeah. So if W is greater than 2 times H, then let PT to be the midpoint. Case 2, if W was smaller than 2H, then this is a kind of scenario that you are happy with going with the area. So find, let's say some P of T such that the area of ST plus is equal to the area of ST minus. Yes.
Should then vector xt be of unit norm?
Should be,
The vector xt be of unit norm?
so it should be a unit vector. Why?
Because if you scale that, I guess your no matter.
I mean, I can normalize the problem at the beginning, but
Yeah, but your loss function would be scaled as well.
sure.
So you cannot set.
Are you saying I should have made an assumption that xt is in unit in 0, 1 to the power t?
xt.
Yeah,
Yeah,
the context. It
it's
doesn't,
not
it doesn't, it doesn't need to
one.
be a unit vector, but it should not be unbound. That's your question. Otherwise, the loss is going to be unbounded by the scale of the context, obviously.
Yeah.
Yeah. Maybe I didn't mention that. Yeah, some of the assumptions are kind of like trivial assumptions. Like for example, the context is bounded. Add that to the set of assumptions that they started with. Every xt should be a vector in unit hypercubed, the d-dimensional vector. All right. So is it clear what does the algorithm do? So if you're in a situation where W is greater than 2H, and the W and H depend on the direction of X, right? So the width is along the direction X. So if your width is large or along the direction XC, which is kind of in example 1, what you do is you basically try to find this midpoint. You don't try to actually target for the area. Like for example, if that was the case, if in case 1, I try to find a PT such that the areas are equal to each other, then if you are in the very extreme case of example 1, then this step, you don't know what to do. It's just like both sides are 0, no matter how you find PT, right? So this is why here I go with the midpoint, not, for example, a point that equalizes the areas, because areas, in the very extreme case, when W is way larger than H, would be 0. So if W is very small and H is large, you're going to be an example 1. And most of these areas are 0. So this kind of search in this case can be meaningless. But then this point is always well defined and you can go with that. But then if you're in the kind of situation like example 2, you somehow know perimeter is not a good option for potential function and you want to make progress in your area. And for that, you make sure the area of the next set is a constant approximation to the area of the current set. And therefore the change in the area will be upper bounded as it will show on the loss. But this is more or less it. Is the algorithm clear? That's it. That's the algorithm. Let's try to analyze it.
Could you repeat why a factor of 2 is important?
Yeah, so because when you're in this, you will see in a second that when you're in this case, kind of the area is upper bounded by W squared. And therefore the square root of area is lower bounded by W squared, order W squared. And therefore the square root of area is order W. And W is a universal upper bound on the loss. So if you ensure that the area of ST plus, the constant approximation of current area, then you ensure that W is going to be a constant approximation of the next area, or the change in the area. Therefore, the change in the potential function is going to be a constant approximation of W itself, and W is an upper bound on the loss. Therefore, you have the potential function. But you will see that in the let me check into the proof of this slide 4. The theorem. To the alg as constant with red for symmetric. So without loss of generality, assume f of t is equal to plus at some time t. I'm fixing some time t. And without loss of generality, I think the feedback you got is a plus feedback. Then the minus feedback would be exactly that. Now, if we are in case 1, meaning that the knowledge set you have at that time has a property that W is greater or equal to H, then let's look at the change in the potential function. So I claim Vt minus Vt plus 1 So I'm going to actually look at, let's say we look at P T minus Pt plus 1, the change in the parameter. So how much the parameter does change? Pt minus Pt plus 1. So you go with the midpoint. So originally this was the parameter. Now you get a plus feedback, so you have to pick this part. So then this is going to be your ST plus, which is ST plus 1. So now your new parameter is going to be this point, right? So previously the parameter was the parameter of ST. This is st plus, this is st minus. So the new parameter is going to be the length of this curve. And if you look at the difference between pt and pt plus 1, what that difference would be? So it would be the difference between, let's say, this and this line. So let me call that L. So L is the, this is L. So pt minus pt plus 1 would be exactly equal to L minus H, right? Is that clear? So again, so we go with st plus because of the feedback sign. Therefore, my original parameter was the length of this curve that is around st. The length of the curve of st plus would be this curve. If you look at the difference, this part cancels, so you end up with L, the length of this curve, minus H. That's now we call to L minus H. And L, I claim it is at least W, the width of the curve, the width of the potato. Why is that? Because also you're gonna move from here to somewhere here, the distance is W over 2, and then you have to come back. Pythagorean theorem, so the total length should be at least 2W. So the shortest way of getting to this surface and coming back is going there and coming back to 2W. So any other curve is gonna have a length that is at least 2W. Is at least, sorry, W divided by 2 plus W divided by 2 which is W. So L minus H, that is W minus H. But we know that H is at most W divided by 2. So this is at least W divided by 2 because of the fact that H is at most W over 2. And so here's the thing. So the W is the width of the convex set. And this is always upper bounded by the loss function, right? Because of the definition of the width. So the width is always pt bar minus pt minus. The loss function is just 1 point. So this is going to be upper bounded by the loss function. Does it make sense? And then the funny part is now I can say the loss function is at most the phi t minus phi t plus 1, simply because the other term in the phi t is also increasing. Area only decreases. So now, in this case, we have the potential function to capture the loss at that stage. Okay, so this is case number 1. Does it make sense? What I'm doing here? So we're considering 2 cases, and in each case, I want to show the loss that you incur, which is always upper bounded by the width of the uncertainty set, or knowledge set, is upper bounded by the change in the potential function. And in case 1, I'm using the perimeter part of the potential function for my argument. And in case 2, as you will see, I'm going to use the area part to finish my argument.
Should that be double? I mean,
LT divided by.
I mean the.
I mean, some constant times LT. You're right. If that's what you need. But that's fine. I mean, think of it as some constant that pt minus h plus.
I think L minus H is more than W itself.
L minus H is more than W itself?
Yeah.
Why is that? I mean, H can be L minus L is just this part of the curve.
Yeah, I know. So.
And you were saying L minus H can be, well, so the extreme case.
It's like example 2, right? It will not be.
I think
This is exactly.
this is the example that shows it's not order W because it's order W squared divided by H. And if H is much larger than W, then you see this is for some reason I actually did this calculation here for that example. Think of the shape to be of this form, right? So here I calculated this minus that. Let's take it offline, but it's not enough to just consider it.
Could you repeat how we go from the difference in BT to the difference in the potential function? Difference of
yeah,
BT.
so because area only decreases, so basically potential function decreases from t to t plus 1 because of two parts. One part is from due to perimeter, the other one is due to the AT. So if you look at the phi t minus phi t plus 1, basically this is at most phi t minus phi t plus 1, because the other term in field is also decreasing, which is the area from t to t plus 1.
We're saying regardless of what happens with the area,
Regardless of what
we're
happens,
ensured at least this.
Exactly. And in fact, we know that in some cases, the area doesn't change much, like example 1. So you need to look at this lower dimensional volume in order to capture the loss using your potential function. Right. So now let's look at the other case. That will finish the proof. So case number 2. So if case number 2 happens, then we know that W is smaller than 2 times H. So here is a very beautiful geometric argument that we found in this paper. So here I'm going to use convexity. So think of your potato. And this is going to be the upper line. This is going to be the lower line. This is the midline. All right. Actually, on a midline, think of the line that has the maximum length. So basically, I move this hyperplane such that the length of this line segment is maximum. The actual section, cross section of the potato. Okay, so this is the picture. So this is the line with maximum section. Cross section. I mean, what's the right word for it? You get the idea. So I'm moving this line until the length of this line segment is maximum. Now, right. So the potato is convex. It's a good potato, so it's convex. If I connect this point, so with these two guys, and I connect this point to these two guys, then I can say the area of the potato is upper bounded by the area of this triangle plus the area of this triangle. So this is area 1, this is area 2. Then I can say the area is greater or equal area of the potato is greater or equal than A1 plus A2. Right, and in fact, I don't need this to be the line with the maximum section. I think I can do this argument with any line. So, sorry about that. Yeah, I think I'm gonna actually look at the line of the theta prime such that the theta prime dot product with xt is equal to pt median, the median. So the one that we had before, this one, the same line. So this is now H. All right, so what can we say about A1 and A2? So A1 and A2 are two areas of two triangles. So this is equal to H times W divided by 2, for example, plus H times W divided by 2, which is equal to H times W. And we know H is greater or equal than W over 2, so this is greater or equal than W squared divided by 2. Because of the fact that in this case, actually H is greater than W. So all I'm trying to say is that as a result, you can say the square root of AT is actually greater or equal than order W in this case. And we know that this is upper bounded by the loss at this time. Okay, now let's see what happens. So if I look at the change in the potential function, Vt minus Vt plus 1, this is greater or equal than the square root of At minus the square root of At plus 1. I'm just ignoring the perimeter change of the potential function, focusing on the area part. And this is equal to the area of At times 1 minus the square root of half. So this is the part that I needed to have a balanced partition, so that I can say the change in the potential function is a constant approximation of the area, square root of area times t, because this is already an upper bound on the loss, and now I can continue the argument. So now this is greater or equal than order width, as we saw there, which is greater or equal than LT, up to some constant. Order LT. So the bottom line is here, we also show LT is upper bounded by some constant times the change in the potential function. All right. And this finishes the proof. Why? Because we had this potential function argument at the beginning that, hey, so if LT is at some constant times the change in the potential function, that means the sum of all the LTs is going to be upper bounded by some constant times the potential function at time 1. And this potential function at time 1 is just some constant, right? The perimeter of, all right, so basically at the beginning, you're looking at the square, S1, right? So the perimeter is, I don't know, 4, this is 1, so this is upper bounded, this is going to be 5 at the beginning. So that gives you a constant. Yes?
Can you please repeat why order of time W is greater or equal than LT?
LT, yeah, because what is the definition of LT? LT is equal to the, we are thinking of absolute loss or the symmetric loss. So it's a difference between the theta dot product xt, the unknown parameter, minus, somewhere that you have picked, which is, let's call it pt, but it is always some point theta t dot product with x. Right, so we call this thing pt, but we can also write always pt as theta t dot xt. Right. Like for example, you can pick this point or you can pick that point.
Yeah, it would be lower bounded by the difference between thetas, order of difference between thetas.
Yeah, okay, I can do what. So here is the beauty of the order function, right? So I can say this is upper bounded by, I don't know, PT bar plus AT underline. Actually, PT bar minus PT underline. It's upper bounded by 2 times PT bar. How about that? So you get the idea. So this is upper bounded by order W.
Why?
Because W is just PT bar minus PT underline. So this is upper bounded by 2 times PT bar minus PT underline.
Okay.
Yeah. In fact, you need to upper bound this by PT bar minus PT underline. And then W is going to be an upper bound. Another way to see that is, theta minus theta t is just going to be a vector whose norm is bounded.
Yeah, but in that case, we actually are using that the direction of xt is on the W side. I mean,
yeah, that's how we define.
Yeah, we are using that fact if we are going to consider the maximum.
Of course, I'm using that fact. Of course, I'm using that fact. So basically, right. So W is the width along the direction of xt. But
that's really what it matters. Not even, no matter how big h is, it doesn't count.
It doesn't. So if W is fixed and h is large, then you're going to a situation where the area can be quite small if W is a small tree. So what is your question?
No, I mean, it's not a question. It's just no matter how big h is, it doesn't matter for loss.
That's true. Yeah. So the upper bound on the loss is going to be W. So you can be in a situation when h is very large and loss is not bounded. I mean, it's not that difficult to see that because this is the effective direction. So this is the direction that can create any kind of loss. So anything orthogonal to that will create no loss. All right. So good. So let's have a break maybe for 10 minutes and then we will be back. 10 is too much?
No. We're overjoyed.
And we talked about what is it? Yeah. Pause this for a second.